Okay, hi everybody. Thanks for joining my talk on real-time data processing. I'm Wolfram from Baqend, and you might remember me from talks such as real-time databases explained from last year's code talk. This year, it's going to be a bit more high-level and about systems like Storm and Flink, whereas last year we talked about Firebase and Meteor and things like that. So before we dive into the actual topic, let me briefly introduce myself. So I'm Wolle, as I just mentioned, and I'm a guy with two hats, if you will, because on the one side, I'm from the University of Hamburg, because I did there my PhD, and researched real-time databases and developed actually Baqend's real-time database, and also was concerned with stream processing systems covered in this talk, and NoSQL database technology in general. On the other side, I'm now working for the web performance company Baqend, and we basically make the web faster, and we do all kinds of cool things there. We have our own real-time database competing with Firebase, and also do lots of things with caching and real-time processing, and that's what we're going to talk about today. So if you're interested in what Baqend is doing, check out our website. We have a cool performance plugin with which you can accelerate your own websites, and it basically makes advanced caching technology available for any website. So check it out. It makes things really much faster. And we also like to talk about our technology and what we do. So if you're interested in maybe doing an interesting project on top of our platform, or have like a talk with us, just contact me. OK, so enough said about the meta information. Let's talk about the talk. This is what we're going to talk about in the next 30 or 40 minutes. In the first part of the talk, we're going to introduce big data processing in general. So we're going to talk about what a data processing pipeline looks like and what different processing models are there, so specifically batch processing and stream processing. And then we're going to talk about how these different paradigms of processing are implemented in real architectures in the wild. And in the second part, we're going to have the system survey, where we're going to talk about concrete systems, so Storm, Samza, Flink, and Spark streaming, and compare them with regards to things like achievable latency and ordering guarantees and so on. So then we're going to have a brief wrap-up where we just talk about what the main findings and takeaways are. And then in the last part, I'm going to talk again about real-time databases, because that's my favorite topic. And that's basically the use case that we at Baqend have for employing stream processing in the first place. So let's start with the introduction now. Scalable data processing. If you look at a data processing pipeline from above, if it looks something like this here, you have data coming at your system from, say, users, or from server logs, or from sensors. And these data items are written to something like HDFS or a streaming system like Kafka. And then they basically wander through your system. You have some kind of processor that generates some meaningful output and writes this output into a serving system such as HBase or Cassandra. And then you have applications that consume these output data. So in this talk, we're going to cover the processing part here. And typically, when you have large volumes of data, you can't just run your processing job on a single machine, but you have basically the necessity to scale that out to several machines. And this process is pretty complex, because you have to take care of things like deployment. So how actually do you distribute the code across a cluster of machines, and how can you start and stop work? Or how can you monitor whether everything is all right, and whether every worker is actually up? And how can you, for example, assign work to individual machines? And how do you do it in such a way that you don't have stragglers and the workload is balanced like homogeneously? And also, if you have an error, so a worker dies or something like that, how exactly can you guarantee that the work is still being done in the end? So how do you restart workers, and how do you reschedule the failed work? And frameworks for data processing, so for example, Hadoop, which is batch-based, or the systems for stream-based processing we're talking about today, abstract from these complexities and basically hide these problems so that you can concentrate on writing application code and don't have to think about too hard about these issues there. So as I mentioned 3 times already, we have 2 basic paradigms how you can process data, and the one is batch processing and the other stream processing. And there's not only these 2 paradigms, but like dozens of systems that have popped up over the last years And each one of them basically follows a slightly different turn in how to process data, and it's hard to basically evaluate which system is best to use when. And you can organize the system, for example, on such a two-dimensional grid here, and we've done that for whether they are geared towards low latency or rather high throughput. Then you just see that you have systems like, for example, Spark or Hadoop. They are basically optimized for achieving high throughput, and you have systems like Storm or Heron. They are rather geared towards low latency. And you have other systems like, for example, IBM Infosphere Streams. They might be optimized for other aspects, such as ease of development or something like that. And it's important to understand which system is basically geared towards what, so that you know which is the best one. So let's start on a high level and talk about batch processing in general, which basically addresses the volume requirement of these three big data V's, like volume, variety, and velocity. And the idea is that you have data that is collected at your persistence layer. It's just written down to your HDFS, for example, and then periodically, so say once an hour or once a night or something like that, you have a MapReduce job or something like that, which then just takes the data and processes everything at once. And it's easy to reason about what you get there, because the job just takes a fixed data input and produces a single output. And it's also very cost-effective and efficient, because the job is just started, then it's running at full speed using all the available server resources. And when it's done, it just stops working. So you can basically get the most out of your hardware. The problem is obviously, though, that you get also very high latency, because if you only process your data once a day or once a night, then you don't have updates in between, and that might be prohibitive for your use case. So then you might be looking at stream processing, and the idea of stream processing is pretty obviously that you have a stream of data items and process it. So you get data items one by one, and then as a data item arrives, your processor takes this item and produces some output. The obvious example advantage here is, of course, that you get low input-output latency. However, you get a number of challenges that are harder to solve for stream processing systems than for batch processing systems. Because, for example, a stream processing job is a long-running job. So, you know, with a batch processor, you can just start the job, and then it's done, and then you can deploy a new version. And the next time you start it, it's a new version of the job. That's not as easy with the stream processing job, because this thing can't go down. You know, you cannot allow downtime, and therefore, it's pretty hard to do something like, for example, a version update of the job and handle failure. So another issue here is that data is arriving asynchronously, so you don't have one huge batch of data items that you can process, and you know it's complete. The data items in your job may arrive out of order or late, or maybe too late, and you have to produce meaningful output regardless. And there are also other things like fault tolerance and state management and restarting failed workers, which is harder to do in a real-time environment than in a batch processing context. So basically what you get here is that sometimes stream processors, and that's particularly true for early systems, they just didn't give you something like state management, and then you had something like a system that produced outputs in real time, but when your worker died, then, well, you just had incorrect results. For example, you have a counter, and your machine dies, and then the machine restarts and starts counting again from a 0. And then your counter was wrong for a time until you reset it to a correct value. So what people ended up doing was something called the Lambda Architecture, and they just took their existing batch processing pipeline, which is the one you see at the bottom, and then they just duct taped the real-time system on top, so that you still have your batch processing that collects all of the data and processes it once a night, but you also have a real-time system that basically incrementally updates the output in real time. And then every time the batch job runs, you override the real-time data with the correct batch data, and then you end up with something that is fast because you have a real-time system, and it's still eventually accurate because the batch processor just overrides the possibly faulty data written in real time. So typical setups would be something like you have a Hadoop and a Storm cluster, or you're using the stream and the batch-based APIs from Spark or Flink. But the difficulty here again is obviously that you have a more complex deployment because you're having 2 code bases and also 2 systems or 2.5 systems or 1.5 systems, depending whether you're using Flink, real-time and batch or what exactly you use, but it's more complex than just using a single system. So what people then tried was something like the Kappa architecture, and this is just a fancy name for stream only with no batch. So the idea is, as illustrated below, you do everything right as you would do it with stream processing. So you get data items and then process them and generate output. The difference mainly is that you have a streaming layer, so a system like Kafka that can replay data. So you get this this ability to replay data items when, for example, your worker dies, and therefore you can recover from failure that you could not recover from if you didn't have the ability to replay data. So this is pretty simple to think about because you only have stream processing and no batch, but it can also be hard to deploy in some cases, for example, because you simply have a batch system that you need to use or that you don't want to get rid of, or you have special tooling in your stack that only works for Hadoop, and then you're stuck with Hadoop, so that can happen. Or you have an algorithm that you want to use for your analysis, and that isn't purely incremental, and you need something like a batch processor, and then you just can't use Kappa. So, but these are the main 2 architectures that are basically used for stream processing. Typical operators that are used in stream processing are basically what you would expect. So you have filter and transform operations. You can group individual items in your stream, and then you can compute aggregates over that, so something like a count or an average or a sum or whatever. And whenever you do something like that, you have to specify a time window over which you do these aggregations, for example. So the most notorious ones are tumbling windows and sliding windows. And the difference basically is that the tumbling window is a discrete time window. So something like if your time window is 1 hour, then it would be from 10 to 11. And when you reach 11, then you start from scratch and consider all the data from 11 to 12. And with a sliding window, you would just always take the last hour, and new data slides in on one side, and old data basically falls off the other side. So, and an example pipeline would be something like this here. That's taken from the Yahoo streaming benchmark. You just read add data from a Kafka cluster and then filter out records that are irrelevant for you, and then you extract the attribute values from these tuples that are relevant to you. Then you group everything by the add campaign, and then you compute something like add view count per add campaign. Yeah. So to wrap up the introduction part, we have in big data processing basically 2 different paradigms. Batch processing is rather easy to reason about and efficient, but has a problem with high latency. And stream processing is basically a contrast here because it gives you quick results, but is more complex to handle in general. And we have two competing architectures to employ stream processing. One is the Lambda architecture, which makes this combination of batch and stream processing. And Kappa architecture only uses stream processing. So, and stream processing is the keyword of this talk. So let's talk about different stream processors. We have different systems that are quite popular for batch processing, so Hadoop, Spark, and various commercial implementations. And we have stream processors, so systems that take data items one by one and then process them as they become available. So, and then we also have like hybrid systems, which are called micro-batch systems. And in this talk, we're going to talk about stream and micro-batch systems. So the thing basically is stream systems process tuples one by one, and micro-batch systems just take very small batches. So that is almost as if you were processing them in real time, because you only wait for a very small time and don't process your data every night, but say every 5 seconds or every minute or so. Yeah, so the first system we're going to talk about is basically the first system that became wildly popular, and that was Storm. It was developed in 2010 by a company named Baqend, and eventually Baqend was acquired by Twitter. It's rumored that the main reason was Storm, because it was so awesome. And what Storm did was basically it provided the first production-ready stream processing abstraction, similar to what Hadoop did for MapReduce, and therefore it was also called the Hadoop of real time. And it's very low level. It's rather, looking from today is rather complex to handle, and you have to do very much plumbing, but you can also tune very much in Storm, so it's still really competitive if you're going for low latency. And by the way, that's the reason why we ended up using Storm over Flink. Yeah, it's used by everybody and their uncle because it was the first production-ready system, and therefore everybody started with Storm, and therefore it's still around today. Yeah, and it has been open source pretty early as well, so it has been around from 2011 to the public. So a data processing pipeline in Storm, or a data flow graph rather, is called a topology, and it looks something like this. You have data coming into the system from the top here, from a system like Kafka or Redis or another streaming system, and the components that pull the data into the topology are called spouts. And the nodes doing the actual computations are called bowls, and they just shuffle the data around until they eventually produce some output and write that to the serving layer or do some other action with that. So what you need to know about Storm is you have these two components, spouts and bowls, and everybody is completely asynchronous. So you don't have any ordering guarantees. Data is just drawn into the topology process and then handed on. And that makes lineage tracking a bit complicated because you have to track every individual data item. Storm does that relatively efficient, and that was a very big thing at the time because it could guarantee that whenever a tuple is processed, it gets acknowledged. And if it doesn't get acknowledged, then you knew, OK, it wasn't processed. Apparently, something died, whatever. Let's replay the data item. And therefore, you could provide at least once processing guarantees. And that was really awesome and helped Storm get traction. So, however, using the lineage feature also doubles the messaging overhead. Therefore, it's sometimes disabled if you have a really high-performance application because it noticeably reduces your achievable throughput if you turn it on. So, a Storm deployment looks something like this. You have a Nimbus, which is basically the job tracker, and you have Storm worker nodes, which are called the supervisors. And all the work is done with the supervisors, and the Nimbus only communicates via Zookeeper with the nodes for deployment. So when something dies in the cluster, the Nimbus can reschedule work. And if the Nimbus dies, but everything else is fine, then you don't have a problem. Something that Storm did not come with out of the box at the beginning was state management. So in the early days, you didn't have state within Storm and had to manage it in your application code. And this was kind of a problem because it's really hard to make sure that once your worker dies, you properly recover from lost state. And in version, I think, 1.0, like 2016 or so, state management was introduced into Storm. However, it's still pretty lame, in my opinion, because it basically involves synchronous states updates to a remote data store like Redis. And that is on the critical processing part, and therefore bites your low latency requirements. So you can really only use it for very small state. Another feature that Storm has, which is quite important, is back pressure. And back pressure means that whenever you have a complex topology and you have several layers of nodes, then it could happen that a downstream node is just overwhelmed by the data, and the upstream nodes don't know about that and just keep on ingesting data. And what you get there is basically a diabolic circle, because even more data is consumed into the topology, and then more tuples time out, and when they time out, they get replayed, and then you just, the overwhelming factor becomes worse and worse. And the back pressure feature, also introduced in 2016, I think, basically makes sure that downstream components can signal to the upstream components that they need to stop ingesting data too fast, and then the topology can basically recover from overload scenarios because the load is reduced until everything is fine again, and then you can just basically hide load spikes without your cluster dying. Trident is something like, I treat it like a separate system here very briefly, because it effectively is. You have an abstraction layer on top of Storm, and it was introduced in 2012 because Storm was so low level, it didn't have state management and didn't have joins and aggregations, and all that comes with Trident, so it's basically an ease-of-use extension. But it has performance problems in comparison, so it's not as scalable and not as low latency as Storm. I only have one slide on that, and basically I want to tell you that it takes a small number of tuples from maybe different data streams, then puts them into one batch and makes sure that each batch is processed transactionally. So you have with Trident exactly one's processing guarantees because batches are executed transactionally, and you also have ordering guarantees between batches. So you know that basically if you put tuples into your data stream and they land in the same batch, then they are processed before tuples coming thereafter. Yes, another system that came from the industry was Samza, and Samza was developed together with Kafka, basically for applications that require large state, because that was something that Storm was not particularly good at, not to say pretty bad. And the idea of Samza basically is that you have Kafka as the log stream system or the streaming system from where data is consumed, and then you process data and write the output directly to another Kafka stream. And within LinkedIn, the idea was that you just had many data streams, like enriched click streams and whatnot, and then your many teams could share the enriched data that the streams basically produce there. So it's also used by many big players, and basically every system here is used by many big players. And it has been around since 2013 as an open source product. And this is how data processing in Samza looks. You have data coming in from Kafka, that's at the top, and then you have a single Samza job that basically corresponds to something like a Storm bold, and then output is written directly to Kafka again. And these bubbles are moving so slow when they're in Kafka is supposed to indicate that this might lead to higher latency compared to Storm, because Storm passes messages around directly between worker nodes. And with Samza, you always have to touch disk, or basically you have to give the data to Kafka and then read it from Kafka again. And that's just slower if you have a long processing pipeline. What's pretty awesome here is that Samza basically keeps the order in which data arrives in Kafka. So if you have a partitioned data stream in Kafka, then you know that the output is in the same order as the input. And it's pretty robust because you don't need, for example, back pressure, because there are no upstream components. Every task just consumes data from Kafka, processes it, and then writes the output to Kafka, and that's basically it. On the downside, however, it's more complicated to build a complex data flow graph because you always have individual jobs, and every hop means you need to write a new data job. What makes Kafka special, Samza special, is its concept of state, because in Storm we saw that state is held remotely, so in a separate key-value store, as indicated on the left here. Samza, in turn, takes another approach and writes data into a local database and just replicates asynchronously the change log to some remote system. So that basically gives you extremely fast lookups because you don't have to go to a remote key-value store. And therefore, you can also have a very large state because it doesn't really matter. You're doing everything locally there. Yeah, as I said, example application would be something like you have a click stream, enrich it, and then write it to some Kafka stream, and the other data scientist teams can just access this stream of enriched click streams and don't have to do that for themselves. OK, so this here illustrates why the concept of local state is pretty cool for recoverability. So what you see here is we have data coming from the top in a 3-partitioned Kafka stream, and then we have 3 tasks that consume these data items from these streams. And the task number 3 just died and is currently recovering. And what a Samza task does when it's recovering is basically it boots up, and then it reads the changelog stream, which is on the bottom right, and just reads it until the end. And then at one point, it knows, OK, I've consumed my upstream data until log number whatever, until a certain point, and then knows, OK, I need to start here, and then it just goes on with processing. And since it replayed all the change logs from above, it basically knows that everything up until here has been processed exactly once or more. So you get at least once guarantees basically for free by using this paradigm here. Yes. So next system in line is Spark, or Spark Streaming, rather. Spark Streaming is an extension on top of Spark, so let's briefly talk about Spark. Spark is often called the MapReduce successor because it makes things like the API a bit better than MapReduce, arguably, and also has other advantages specifically for iterative algorithms. Yeah, and it has huge traction, so many developers are contributing to it and are using it. And yeah, it's basically the standard tool, I'd argue, for batch processing nowadays. So it has been around since, I think, 2009 or 10, because it has been developed around that time. It's coming from an academic context, was developed in Berkeley. Yeah, and it's still thriving. And Spark Streaming is one of the standard libraries. There are others for example, machine learning or SQL or graph processing, but Spark Streaming is the real-time library there. And the idea is basically that you take the batch processor, Spark, and just chop up the batches into very small batches and process each batch on its own, yeah, relatively identically to a normal batch. But since the batch is very small, you get very small input-output latency. So since you're using the batch processor, you get very rich guarantees. So for example, exactly once guarantees, and you also have stateful computation here, which is pretty nice. So the underlying primitive in normal Spark is called a resilient distributed data set, or an RDD, and that's just an immutable collection. And when you do some kind of processing in Spark, you just apply deterministic operations to an RDD. So that basically means that you transform and map and filter and reduce and whatnot your RDD, and the system keeps track of the lineage of these operations. So basically, the chain of commands that you have been using to transform your data. And this means that whenever something fails, it knows basically what it has to do to reproduce all these steps, and therefore it can make sure that it just retries until it works, and then you get exactly one's processing guarantees because you can repeat everything if something goes wrong. And the primitive used for Spark Streaming is called a dstream, which is a discretized RDD. And as I said, it's just chopping up the stream into batches and processing these batches. So since there's some overhead associated with batch scheduling, you don't really get below 100 milliseconds, and it's rather designed for latency on the order of 2 seconds. So if you're going really low, you wouldn't use Spark Streaming. But if second or few second latency is OK with you, it's a pretty nice system to use. And here's an example of how the code looks. And it's really pretty awesome if you know how Storm code looks in comparison. So in this example, you just count page views. And in the first line, you basically declare that you read page views from some endpoint in 1 second batches. And in the second line, you just say, OK, and now we've got events. And for every event, there's a URL, and we just associate, or we just have these tuples that we produce from our page view stream, where we have a 1 for every URL. And in the next line, we have this counts stream, where we basically reduce it in such a way that we count the ones for every URL, and then end up with a tuple stream, where we have the URLs and the number of counts next to it. And under the hood, Spark would then just do everything it can on the same machine. So for example, the page views in one step would be executed on the same machine. And then for the reducing step, we need to shuffle around the data, and that would happen transparently. So you wouldn't have to think about that in Spark, and you would have to think about that very much in Storm. So last system in this comparison here is Flink. It's also coming from the academics. It has been developed in Germany and several universities and institutions in Berlin, more precisely. And it basically, I'd say it tries to push all the right buttons because it combines the feature richness and library richness from Spark with low latency comparable to Storm. And the thing is probably that it has just been too late to get traction as strong as that of Spark, because now everybody already has a Spark cluster. But yeah, people are getting there, and I think Flink is really remarkable because it is extremely sophisticated. And this diagram here illustrates that you have basically an adapter for everything. You have a natively streaming runtime environment. And on top of that, you have a streaming and batch API, so the data stream and the data set APIs there. And on top of those, you have libraries for complex event processing and even a Storm compatibility layer, and yeah, basically everything you might imagine, probably. Yeah, so you could talk about all day about Flink, but I think I would like to talk about state management because I think that's a really cool feature in comparison to the other systems here. And the idea of Flink state management is that it has some state backend, for example, RocksDB, and asynchronously writes snapshots to some remote storage, and thereby achieves exactly one's guarantees. Basically in this fashion. You can imagine you have a data stream. That's the stream of these yellow rectangle thingies there. And occasionally, Flink just inserts some kind of barrier. So that's a watermark and just tells the receiving components that they need to snapshot their state now. And then they write off their current state asynchronously and write state updates using a copy on write data structure. So when every node basically is done with the snapshot for a particular barrier, then you have a distributed snapshot of your entire system somewhere lying in your HDFS. And when some worker dies or something like that, you could just basically restore the state to one of those barriers and replay the data from there. And then you know that in the end, you just processed every data item exactly once. So this is how you get exactly once guarantees with Flink with a very low overhead approach. OK, so let's get to the wrap-up, because I want to talk some more about real-time databases. Yeah, so if you put all of what I said into a matrix, you get something like this. So you see that in the left most column, you have several qualities that are interesting. For example, the strictest guarantees. Basically, every system supports at least once processing, and latency and state management and whatnot. And in the columns, you have the different systems. And it's pretty hard to talk about all this. What you could remember is something like Storm was very early and is extremely good at latency, and that's basically it. Trident is probably a system that you wouldn't use today because you could use Flink. And Samza, Spark streaming and Flink streaming are good for large state applications. And it probably depends on your personal taste what you're using here. Overall, I think on paper, Flink is probably arguably the best overall package. And it's only slightly worse in latency than Storm. So in the words of the Yahoo benchmarking team, you could say that Storm and Flink show sub-second latencies at relatively high throughputs, with Storm having the lowest 99th percentile latency, and Spark streaming supports high throughputs, but at a relatively higher latency, which also does not come that surprising because it's a batch processor. So there is a bunch of other systems which we could be talking about, but we don't. We've written articles on that, so please check out our company blog if you're interested in that. And now let me spend the last few minutes on real-time databases, because that's where we think the future of streaming data processing is going. And to illustrate what a real-time database is, let's briefly talk about what a normal database is. So a normal database is a static data repository which you can ask questions about the current state. So imagine you have a database that stores different shapes like rectangles, triangles, and circles. And then you have an application that just displays all the circles that are in the database. So the application just queries the database for circles. There are none, so we don't display any circles. And now the client does whatever, and in the meantime, things keep happening on the database side. And then the client asks again, and gets another query, and this time the green bubble is there as well. But the thing is, the client never knows where the stuff changed, and to find out whether the current, the current known state is still the actual state, it has to repeat the query. And the thing is, it can do that, and it will get the response. But the thing is, now the green bubble, for example, was already known and was transferred nonetheless. And the database had to execute the query, and even if nothing had changed, the system still would have produced the result and would have sent that over the wire. And that's pretty stupid. And it's also pretty inefficient. And you basically have to trade off the database workload and the network traffic against the degree of staleness that you're willing to accept. And what you actually want would be something like this. Imagine you have an application where you just track your employees, because that's what we all would like to do to make sure they're actually working. And then we have, there's actually some kind of looks like our office, basically. You have this grid at the bottom where you see the coordinate system, and you can see where everybody is currently. And we're interested in keeping the guys in the room B, and that's why we write this query on the top left. And while people are moving about, our CEO basically has this UI where he sees where everybody is, and then he sorts them by name. So you can see that it's live updating, and when somebody enters the room, now the yellow bubble there, for example, the UI updates as well, and when he leaves the room, the UI updates as well. And that's basically something you want because you only want to write the query, and you say, OK, I want to know the result, and I want to know when it changes. And I don't want to do all the hassle with repeated polling and diffing results and whatnot. And that's basically what real-time databases do. So you have purely pull-based databases on the one side, and you have the purely push-based systems we've talked about here on the other side. And in the middle, you have real-time databases. And Baqend is such a real-time database. And there are also other systems, and those are the ones that I've talked about last year. For example, Meteor, RethinkDB, Parse, and Firebase. And all of these systems have severe problems. For example, none of them scales sufficiently. And also, excluding Meteor, they don't really support sufficient query expressiveness. And we developed Baqend to basically address all these issues. And on the last slides, I would like to show you how we do that and how that actually makes the web faster. So to explain this, I got to talk about what Baqend does. And Baqend basically removes this problem here, so slow loading times. Because there are many studies about how slow loading times affect your revenue. And for example, Amazon says that when a page takes 100 milliseconds of additional page load time, it costs them something like 1% of revenue. And similarly, Yahoo says that 400 milliseconds additional page load time costs them 9% visitors. And Google found out that when they take half a second longer to assemble the search result, then it costs them 20% in traffic. And that's pretty tremendous. So what's the problem there? The problem basically is that when a user accesses a website, there's first the way to the server, then some back-end processing. And when the server has assembled everything, it needs to send back stuff to the user. And depending on the distance between client and server, that can take time as well. So the obvious solution that everybody already is using is caching. So you have the user just access data nearby from some cache, and that makes it faster because you have lower latency, and it also unburdens the backend because there's less processing in the backend, because many requests don't reach the backend and are just answered by the cache. So the question is, how can you cache as much as possible? Because mostly you only cache static assets, because dynamic data are really hard to invalidate. So if dynamic data like postings or articles or query results change, you don't really know that in the backend. And the magic of what we do is basically that we have developed an algorithm how we can keep track of all stale caches in the world and just invalidate them as soon as they become invalid. So like 30 man years of research, or probably more, went into this. And to illustrate why this real-time database thing is important here, consider something like this. You have a shop, and your users don't just point access your individual products. They ask questions like, can you give me, please, all matching articles here that are currently in stock. Then you type in some search query and get some list. And now for every write operation, so whenever an admin or a user writes something, maybe changes the product description, or whenever something is bought, you have to check whether this write operation to the database adds or changes or removes something in this query. And if so, you have to invalidate all cached copies of this query result. And what you need to do there is a database that can keep track of changes of query results. So and this is what we developed for Baqend. So you see that we have the Baqend application server in the middle, data coming in from the top left, and there's a client on the top right. Could be a user subscribed for real-time results, or could be a cache subscribed for cache invalidations. And in the background, we have our stream processing cluster. So that's an Apache Storm cluster there. And whenever data is written to the database, the application server just passes down the data to the Storm cluster, and the Storm cluster matches the data item against every subscribed query. And these can be like dozens of thousands at a time, and then checks whether the write operation affects any result. And if this happens, and it's going to happen here, yay! Then Storm updates the internal representation of the query result and basically sends the information that needs to be done to update the result down to the client. So only the change delta, nothing else. Or it invalidates the cache. And since we mainly do database query invalidation with this thing here, we call it InvaliDB, and it keeps the database up to date. So we implemented that in this way, and it's pretty special because we partition workload in a way that nobody else does. You see that there are 9 gear wheels, like 3 by 3, and you see that they are organized in a matrix. And the columns there are query partitions, and the lines are object partitions. And whenever you register a real-time query, the query is given to every node in the corresponding query partition. So you hash the query, and then just give it to 3 nodes. So every node now only has to handle a third of the query load, because when something is written, the write operation is also hashed, and then you also just give it to 3 nodes of these 9s. And you see that there's always basically the intersection between the query and the object partitions. And that basically tells you that every object that is written is matched against every real-time query. But we can increase for example, the number of sustainable queries by adding more query partitions, or we could increase the sustainable write throughput by adding more object partitions. And this basically means that Baqend's real-time database can scale with both queries and with writes, and that's something nobody else can. Yeah, as I said, we built that on Apache Storm because it gives you very low latency, and therefore everything is Java. And we implemented that for MongoDB queries, but the query engine is pluggable, so we could also implement it for example, Postgre or whatever you want. Yeah, these are just some performance numbers to show you that it scales linearly and that you have very low latency. So even if you have something like the 99th percentile latency, you are well below 30 milliseconds, and it's really fast. And we don't only invalidate caches with that, we also use it for real-time queries, as I've mentioned numerous times by now. And the API basically looks like this. We have a JavaScript client, and you can just build your query with this builder pattern here, or you could just throw in a MongoDB query, so we also understand native Mongo queries. And then you have your query object and call a function on that object. So either you call .resultList and provide a callback function that would take the result, so the result list once you get the query result from the database, and then it renders your website, for example. Or if you want the real-time query, you basically do the same, but you don't write .resultList, you call .resultStream. And that, again, executes your callback function once when the result arrives and whenever there's a change. So it's basically trivial to use, and it makes your application real-time without you having to understand how that all works. So to illustrate that, we built something called Troogle, which basically works similar to Google, only over a collection of Twitter messages. So that's something we show here. You see on the right and on the left, we have the unfiltered stream at the moment. And then on the left, we start just typing a search query. So we type Java. And now the application only shows you the Java tweets. And you see on the right, stuff is still happening. And on the left, it seems that nothing is happening. But actually, it just waits for the new Java tweet to arrive. So if something is tweeted with Java, that's the case, then we get an update on the left. And we can also paginate through the result because our real-time queries support limit and offsets. And that's pretty awesome because, for example, Firebase wouldn't do that because you don't have content-based filtering, and you also don't have real offsets and limits. Yeah, you do have limits. OK, so that basically concludes my talk. We've seen stream processors in action. We've seen that you could say they are either geared towards low latency or high throughput, but there are other qualities of interest as well, and you should thoroughly consider what exactly your use case is if you choose such a system. We think that for developers, it's important to basically merge the notions of static and streaming data. So we think real-time databases is a thing that's going to be happening soon, and it's going to become more popular. And I would be delighted if you checked out the slides at slides.baqend.com, read our company blog, or just drop me a line if you are interested in the topic. Yeah, thank you. Are there questions? Come on, you can't have no questions. Yes. The question is, can you use it with different languages that are not Java? So what specifically is it? No, I mean, what can you use? Like stream processors? Yeah, basically we have a JavaScript SDK for convenience, but our basic protocol is based on WebSockets. So we have customers, for example, who implement something in Xamarin, C Sharp, and we also have a Java client built for ourselves. So you can use anything that can do WebSockets. Is there another question? Yes. How much storage do we need for the database? For which database specifically? So storage, well, actually, it works like this. We have a MongoDB database, and whenever you register the query, then we execute the query once against the MongoDB, and from then on, we just keep everything in memory. So we don't really have storage. It's just main memory within the Storm cluster. And as I mentioned earlier, Storm doesn't have state management, so you might think that's a problem, but it's actually not that bad of a problem because we just discard data whenever the client connection drops, for example, and then resubscribe because that's a rather lightweight process. So we don't need to store anything apart from in main memory. Is there another question? OK, then thanks for sitting through this talk, and enjoy the rest of the evening. I'm sure I will.